Welcome to Hyperphysics. In this tutorial, I'm going to discuss a very important problem in physics, that is the oscillating piston problem. I'll show you a method that you can use to solve this problem very easily. So let's get started. So the question is given like this. A monoatomic gas of volume V is in equilibrium in a uniform vertical cylinder, the lower end of which is connected by a rigid wall and the other by a frictionless piston. The piston is pressed lightly and released. Assume that the gas is a poor conductor of heat and the cylinder and piston are perfectly insulating. We have to find the angular frequency for this system. So diagrammatically we can see this figure like this, right? So you have gas inside the system and the system is well insulated and there is the piston that is moving. So if you are using the normal method like finding the change in volume and change in pressure, that will take up a lot of time to solve this question. So what I'm going to propose is that we can use something called as the relative error method to solve this problem. Relative error method. So how to do this question using this method? Okay, so the system is already given like this, right? From the question, it is clear that the system is an adiabatic system. Adiabatic system. So it should follow the laws of adiabatic systems. So we have the volume here. So relating to that, we have a pressure. So there is a relation between PV for an adiabatic system, that is PV raised to gamma is a constant where gamma is Cp by Cv, right? So what we are going to do now is we are just going to write from this equation, we are going to use this method. So PV raised to gamma is a constant, or P is proportional to 1 by V raised to gamma, that is P is proportional to V raised to minus gamma, right? Okay, so again I'm going to write this by using this method. I'm going to write this equation as delta P by P is equal to minus gamma delta V by V. This is a basic principle of relative error analysis or relative error method. So from this equation we are getting this equation, and now we are going to solve this equation here. So that is delta P can be written as minus gamma delta V by V times P. And we know that the area of cross section is constant. So we can write volume as area times the length, or the differential volume can be also written as A into delta X. It's the same thing, right? So I'm going to replace this delta V by this equation, that is delta P is equal to minus gamma A times delta X and P by V. Now we know that P is force by area. Here force is mg and area is A. So I'm going to write this as delta P is equal to minus gamma A delta X times mg by A into V. Okay, now what we are going to do is I'm going to rewrite this as delta P. I'm going to take the A to this side. Delta P into A is equal to minus gamma A mg by V times delta X. So delta P into A is delta F, right? From this equation itself, it is very clear. This delta P into A will be delta F for a constant area of cross section. So that is delta F will be equal to minus gamma A mg by V times delta X. So now we can see that this is of the form F equal to minus Kx. So this, from this analogy, we can write this as K, right? So K will be gamma A mg by V, or the frequency omega square can be written as K by M. So that is, from here it's very clear that you can write gamma A G by V is the omega square, or omega will be equal to square root of gamma Ag by V. So let's go back to the question itself. The question is given as for a monoatomic gas, right? So for monoatomic gas, gamma is equal to, for a monoatomic gas, it's 5 by 3. So we just substituted here. Omega will be equal to square root of 5 by 3 Ga by V. So this is the answer for this oscillating piston problem. So option A will be the correct answer. So if you are using this relative error method, you can solve other questions also, but this is a very powerful technique. Everyone should be very careful about this technique. So I hope you like this video. I'll be posting more and more videos every week, so stay tuned. Thanks for watching. So thank you.